after the move instruction, next we will look into the timing diagram corresponding to the MVI instruction. So, difference from the previous instruction is that move instruction was a single byte instruction, size of the instruction was 1 byte. So, when you do the opcode fetch, so you get the full instruction, but here that will not happen, because now this will be it will try to it has to get 2 bytes, because if you look into the code of MVI. So, MVI, say for example, this instruction MVI A 45 hex. So, if the location memory location is A000, then this the code of this is 3E, the MVI A code is 3E, and the value, the next value 45 also has to be there. So, this is a 2 byte instruction, where the first byte is 3E, second byte is 45. Okay. So, in the memory, the location A000 will have the value 3E, and the location A001 will have the value 45. So, for fetching the instruction, so I first in the first cycle I will get the value 3E, and after getting the 3E, in the decode phase we will understand that okay, it is the instruction to move some immediate value to the accumulator. So, the next the processor will understand that now I have to get the immediate value from the memory. So, this is another memory access that will be required, and in that memory access, once the value comes to the processor, the 45 comes to the processor, then it will be put into the accumulator. So, that is an internal operation. So, that is that can be done, but as far as the outside world is concerned, so you can see the sequence of control signal activations like this. So, for the first part of the instruction, so it is same as the previous one, that is opcode fetch. So, only thing is that the similar with the higher order address bus as A0, lower order address bus as 00, the ALE signal is given at T1, and so the value get latched, this 00 gets latched onto the address latch, and then this read bar signal is given. So, the memory will put the value 3E onto the data bus. So, 3E comes to the instruction register. So, it is decoded at this time. Okay. So, at the time T4 the instruction is decoded. So, after decoding, the processor understands that I need to fetch the immediate operand, and as soon as the memory the processor has done a fetch, this program counter value is automatically updated. So, at T4 the program counter value is also updated. So, the program counter now contains A001. So, now it goes to another cycle which is known as memory read cycle. Previous cycle was opcode fetch cycle, this cycle is called memory read cycle. The operations are more or less similar. So, the higher order address bus contains the higher order address byte, that is A0, lower order address bus contains the lower order address byte, that is 01, ALE signal is given, and this read bar signal is given here. So, as a result, the processor will the memory will respond with the content of memory location A001, and that value is 45. So, that is available onto the data bus. So, this value will reach the again the internal inside the processor, and once it is inside the processor, the decoder, the instruction control, the decoding and control logic, it will understand that these values should go to the accumulator, and that is done sometime here, though it is not documented. So, sometime here that operation will be done, because 45 is available inside the in the internal data bus of the processor. So, that will be copied onto the accumulator register. So, this way it is done, and this does not require any further decoding. That is why we do not have another clock cycle here. So, 3 T states are sufficient. So, for opcode fetch we require 4 T states, for memory read operation we require 3 T states. So, this way depending upon the complexity of the instruction, so you may require more number of clock cycles, more number of T states. Now, so this part, so this T1, T2, T3, T4, so this is called opcode fetch cycle. It is also called a machine cycle. Similarly, this memory read cycle, so this is also called a machine cycle. So, we have got these clock cycles. We have got these clock cycles which are we have got these clock cycles which combines into something called machine cycle. This is something called machine cycle, and this machine cycle, there can be several types of machine cycles, like this fetch is a type of machine cycle, then memory read is a type of machine cycle, okay. Then memory write is another type of machine cycle, okay. This memory write is another type. Then we can have different types of machine cycles. Then when we look into this IO operation, then we will see that IO cycles, there are different type of machine cycles like that. So, this way we can have different types of machine cycles. We will look into some more examples, like say say the next instruction that we will look into. Next instruction that we will look into is the LXI instruction. Okay. So, this is more complex, where this LXI A F045 hex. So, it is load extended immediate. So, assuming the same thing, that this instruction is located at memory location A000 hex. So, and this code of LXI A you can find from the manual, that is the value is 21, and this F045 is the 16-bit value that which gives the address from where the A register will be loaded. Okay. So, that was the meaning. So, it is load extended indirect actually. So, that is giving us the this is the address from where it will be loaded. So, how this will be executed? So, this will be executed by some opcode fetch and read cycle, write cycle, like that. So, what is done? First this opcode fetch cycle. So, this is giving us this value, this A0. So, that is on the higher order address bus, and 00 is on the lower order address bus. So, this is ALE signal is given, read bar line is given. So, that is getting the value 21 hex onto the address bus. Now, so this is the 21 hex that we have got, the 21 hex will be on the data bus. So, this 21 hex comes to the instruction register. So, the instruction decoding is done in the cycle T4, and once it is done, then it understands that I need to I need to do 2 more memory cycles to get the full instruction. So, this 45 hex that is so this is so again this address was 00. So, that is incremented. So, it becomes 01. Higher order address bits remain unaltered A0. So, this higher order address bus, it has got A0, lower order address bus has got 01, and again the read bar signal is given. So, sorry, ALE signal is given and the read bar signal is given here. So, as a result, the memory puts the value 45 hex onto this data bus. So, this 45 hex comes inside the processor, and then I have got the other byte has to be loaded. So, this is this 02. So, that is this PC value has been updated, like every time it the processor does an instruction fetch. So, this PC value gets updated. So, PC value is updated to 02. So, this is getting the PC value there. So, it is getting 02 here and A0 here, and the ALE signal is given, memory read bar signal is given, and it gets the memory will put F0 onto the data bus. And for this entire operation, this write bar signal is kept high and IO M bar line is kept low. So, it is a memory operation. So, this is the 3 machine cycles that are needed. So, opcode fetch followed by memory read followed by another memory read. Okay. So, next we look into this move A comma M instruction. So, this is basically somehow I need to access this memory, and the address of the memory is available in the HL register pair. So, this HL register pair acts as this HL register pair acts as the pointer, like in the previous instruction. So, this LXI this should be LXI H, not LXI A, this should be LXI H. So, after these values are available 45x and F0x. So, these two values will be loaded into the HL register pair. Now, this instruction move a comma m. So, this here the HL register acts as the memory pointer and that value is loaded onto register A. So, how this will be done? First, this instruction has to be fetched. So, that is an opcode fetch operation, and after the the code of this instruction is 7E. When it comes to the instruction decoder, so decoder will understand that I have to access memory once again to which location? The location whose address is in HL pair. Okay. So, that is exactly what is done in the instruction. So, let us see how is it working. So, you see the first part of the instruction execution is same as the opcode fetch cycle. So, it is higher order address bus as A0, lower order bus has got 00, ALE is given, read bar is given. So, the 7E, the opcode of this instruction is available onto the data bus. So, that goes to the instruction decoder. In T4 the instruction is decoded, and now the processor understands that the HL register pair content should be used as the address from the memory location from where the content has to come to the accumulator. So, this H register value is put onto the higher order address bus, L register value is put onto the lower order address bus, and the ALE signal is given. As a result, the address bus of the memory will have the HL register value into it, and this now when the read bar signal is activated. So, memory will give the content of that memory location which is pointed to by the HL pair, and that content of the memory location will be available here, and that after it has come. So, it will be immediately loaded into the A register. So, again the same thing, that opcode fetch will take 4 cycles and this memory read operation will take 3 cycles. That way this move a comma m instruction will be executed. Other way, so if I consider the instruction move m comma a, that is the content of this accumulator should go to the memory location whose address is pointed to by the HL pair. So, now we have got an opcode fetch operation. So, opcode fetch cycle where the content from the memory will come to the processor, and this will be followed by a memory write operation where the content of the accumulator register will be written into the memory location whose pointed to by the HL pair. So, the coding for this move m comma a instruction is 77. So, the timing diagram will be looking something like this. So, this is the A0. So, A0 is the higher order address bus content A0, lower order address bus contains this 00. So, this value should not be 7E, this should be 77. Okay. So, there is some mistake here. So, this value should be 77 because the data bus memory will put the content of location A000 onto the data bus, and that is 77. So, once the 77 comes to the processor, so processor will understand that it is a move m comma a instruction. So, in the time cycle T4, clock cycle T4, so it will understand that it is a move m comma a instruction. Now, it has to put the content of accumulator onto the memory location pointed to by HL. So, how to do that? Again the same thing, that this H register content is put onto the higher order address bus, L register content is put onto the lower order address bus, and this content of so ALE signal is activated. So, the address gets latched onto the address latch, and after that the processor will put the content of A register onto the data bus and give the write signal. So, this write bar signal is low here, you see. So, it is a memory write operation. So, the content memory will get this address part and data part and the write signal. So, as a result the value will be written onto the memory. So, this is called a memory write cycle. So, we have seen memory read cycle. So, this is a memory write cycle. The difference is that instead of the read bar signal going low, write bar signal will go low. So, that is the timing diagram for move m comma a. So, this way if you look into the manual of the processor for every instruction, so it depicts the timing diagram. So, that tells like how individual instructions are executed by the processor. So, exact control signals that are going to be activated, that are visible from the outside, how are they activated and what are the values. So, that can be seen from the timing diagram of the instructions. Next, we will introduce another very important concept that is used in assembly language programs, or for that matter it is a very important part of any program implementation, maybe high level, maybe assembly level, but this is very important. Why is it so important? So, we will see it slowly. So, this is the stack. So, stack is an area of memory identified by the programmer for storage of temporary information. So, this is a last in first out structure. So, what happens is that you can say many times what happens is that when I am writing a program. So, if this is the body of the program, then we in any language. So, maybe it is in assembly level, maybe it is in some high level language or whatever it is, we write some procedures separately or subroutines, sometimes they are called subroutines, sometimes functions are. So, maybe at this point I call this procedure, and meaning that this part of the procedure will do the calculation, and once the calculation is over, the control will go back to the next instruction into the program onto which this was, from where it was called. So, this is a very important feature, but how do we implement this thing? So, when the computer or the processor was executing say the code here, so it was doing it in sequence. So, the PC value was just getting incremented sequentially, but when this has to jump to this, then after this so it has, so this point is easy, like I can load the program counter with the value of this location, like if this is the full memory and in this part of the memory. So, the main program, this one has been loaded, and say in this part, so this procedure has been loaded. So, going from here to here is not a problem, because I can just load the program counter with the value of this address, so that it will next execute the instruction from here. But for going back, how do I go back from here to the point from where it was called? Okay. So, for that purpose I need to remember the point at which this program was called. Okay. So, that is done by means of this stack. Okay. So, this subprogram implementation or procedure implementation. So, this is going to be an important operation in the for any programming language, and then the stack will be required. So, the stack normally grows backwards into memory. So, it is what it means is that if this is the memory, if this is the memory, so we define a portion of it, as stack. So, if this is the memory, so we say that so this is the bottom of the stack. So, at this point the stack starts at this point. So, this address may be say 2000 hex, this may be 2000 hex. Now, as you are putting more and more element into the stack, so the stack will grow in the upward direction. So, 2000 next will be say 1 FFF. So, that way it will go on decrementing. So, the size of the stack will so the stack will grow backwards towards the lower addresses in general. Okay. So, that is a normally that happens, but it may or it is not that it cannot grow the other way. So, for most of the processors, so it is done in this fashion, but that is not mandatory. So, programmer defines the bottom of the stack, and stack grows up, reducing the into reducing address range. So, this address values will decrement as the more and more elements are put into it. Now, the next we will look into how this stack can be useful. Okay. So, given that the stack grows backwards into the memory, so it is customary to place the bottom of the stack at the end of memory to keep it far away from other user programs. So, what happens is that say in 8085 we know that the total address space is address range is 00000 to FFFF hex. Now, if I assume that this we have got entire memory space occupied by physical memory chips. that is it is not that the actual memory system has got less than 64K. We assume that the memory system that has been integrated with the processor, it has got 64K space fully available. So, all the places are valid. So, there is no gap in the address space. Then in that case, so what we will do, we will initialize this stack pointer with the last the highest address in the address range. So, if everything is there, then it will be FFFFX. So, if the last memory chip is not going up to FFFFX, if it goes say for example till say 6000, in that case the stack pointer is generally initialized to 6000. So, it will be done like that. So, there is a special register called stack pointer which is used for this stack operations. So, the instruction LXI SP FFFFX, so this will load the instruction load the stack pointer with the value FFFFX, and then from that point onward, so we can use some instructions. There are push and pop, there are two instructions in 8085 by which you can save some values onto the stack or you can retrieve some values from the stack. So, the push means we are storing the value onto the stack, and pop means we are trying to get the value out of the stack. So, they work with register pair only. So, it is so you cannot push pop a single register, like you have, if you do a push operation. So, you cannot say push only the B register. So, you have to push the BC pair, you have to push the D pair, HL pair, and for the accumulator and the status register pair. So, this push, so how this push B instruction is executed? So, first the stack pointer will be decremented and the content of the register B will be put into the memory location pointed to by SP, and then this B register will be that value will be coming will be saved into the stack. So, what is it like, say if this if the currently the stack is the current stack is like this. So, this was the bottom of the stack pointer was pointing here, and if I have got this operation, this push B instruction, then this B register content will be coming here and this stack pointer will be decremented. So, stack pointer will now point to the previous location. Similarly, we have got this pop B instruction. So, this pop or pop D instruction. So, it will copy the content of the memory location pointed to by a stack pointer onto the register D. So, that will be there. Now, other than that, we can have so other than that, so we have to understand the style in which these operations are done onto the stack. So, during pushing, the stack operates in a decrement and then store style. First the stack pointer value will be decremented and then the value will be stored onto the stack. So, at the beginning there is nothing in the stack. So, the stack pointer is FFFFX. So, then the value will be decremented, it will become FFFFE, and then the value will be stored. Similarly, on the pop operation, the stack operator first it will use the value use then increment style, that is the information will be retrieved from the top of the stack and then the pointer will be incremented, so that it goes to the next location, and the stack pointer is always pointing to the top of the stack. So, that way the push pop both the operations, so they are from the top of the stack. So, it uses a last in first out structure. So, the order in which the push and pop are executed, they must be opposite of each other. So, otherwise the values retrieve will not be the same, like here if you have done push B, push D like that, then at the end. So, if you want that this D value whatever was there at this point should be getting back the after executing this code. So, D value might have been modified. So, if we want to get back the original D value that we had pushed here, then I should do a pop D. So, this value from the top of the stack will go to the D register, and then we can have this pop B. So, this value will be popped and stored in the B register, and if you change the order. So, if you do a pop B here, then what will happen? Content of D register will come to the B register instead of going to the D register. So, that way this order is very important. So, you push in one order, and while retrieving you retrieve in the other order to get the original information back. Now, it is addition, there is another register pair which is called PSW. So, this is the register pair made up of accumulator and the flag register. So, the two registers, accumulator and flag register, they make up this PSW register, and this PSW. So, you can push this PSW onto the stack and do whatever operation and then pop it off. Just like any other register pair, this PSW will act as another register pair. So, accumulator and status register, the status of the flag, so they will be saved. So, if you are doing a push PSW, and if you want to do a pop PSW, then those values will be taken from the top of the stack and loaded into the A and PSW register, status register. Now, these stacks are useful when we are going to implement the subroutines. So, subroutine, as we know, that this is a part or the procedures in high level languages. So, they are often known as procedures or functions. So, it is a group of instructions that will be repeatedly used repeatedly in different locations of the program. So, instead of writing it several times, so we write it once, and then it is called from different places. So, like say this one. So, I am writing a program, and in that program, so we have got in this program at several places I want to use the small routine. For example, maybe I want to compute the square root of numbers at different places in the program. Okay. So, what we do, instead of repeating that square root routine at every place, so we write a separate square root plus subroutine, and wherever I need to calculate the square root, so I call this routine. Okay. Similarly, say again at this point it is necessary. So, again I call this routine. So, it will be executing there. So, this way at every point I want to use this routine. So, I can just give a call to that. So, that way it will save the space, because I do not I am not writing the code again and again. So, that way it is going to save the address space, the program size will be less. Now, so in assembly language, so this subroutine can exist anywhere in the code. However, it is better that we put the subroutines at the end of the main program. So, first we put the main program, then we write the individual subroutine. So, that is the standard practice, but ideally there is nothing wrong in putting the subroutine at any place in the program.